So welcome back, Space Explorers. All right, so today we're going to talk about route stability criteria as it exists as a very, very powerful tool to assess very quickly the asymptotic stability of any transfer functions. Now, for all practical purposes, obviously, we will be interested into assessing the stability not of our open loop transfer function, but rather the asymptotic stability of the entire closed loop control system. So for that purpose, I want you to understand the difference between what we did in the last lecture and what we're going to talk today in terms of the element needed to do the analysis, okay? So last time we talked about the steady state tracking error and made the relationship to the system type. Now the system type was a number of integrators or a number of poles at the origin of the complex plane, if you remember the discussion we had. But that was of the open loop transfer function. Okay, so we're calculating direct path from reference signal all the way to the output of the plant. We called that the open loop transfer function, and that was the basis of our analysis because the type of the system was related to the number of integrators of the open loop transfer function. Now today, the tool we're going to talk about, route stability criteria, we need the closed loop transfer function because for practical purposes, we'd like to analyze the analytical stability of the closed loop transfer function. The stability of just the open loop is not very of our concern here, okay? So let's just keep that in mind as we move forward. And that'll be in 5.6. So route stability criteria. Well, you may say, well, hold on a second. We know already how to assess the asymptotic stability of any transfer function, right? All we have to do is to solve the characteristic equation for the roots, or look at the denominator of a transfer function and look at whatever cancels the S terms, right? The poles of the system. Yeah, correct. But if the characteristic equation or the, again, denominator of a transfer function set equal to 0 happen to be of an order 7, well, doing that by hand would be kind of a tremendous amount of work, right? Because you need to extract the roots or all the terms that would cancel this polynomial by hand, and you have to solve for 7 roots. Not very easy to do by hand, especially during an exam when the stress level is relatively high. As an alternative, route stability criteria will allow you to assess the stability or asymptotic stability of any transfer function just by looking at its characteristic equation, and regardless of the order of this polynomial, you'll be able to use this tool and very quickly say, yeah, this is asymptotically stable. Oh, no, that 7-ordered polynomial, my characteristic equation, has 2 poles on the right-hand side of the complex plane. I don't know where, but I know that there are 2 poles that are going to be unstable. Okay, so that is the reason for using this particular tool that we're going to talk here today. All right, so to begin with, you need to solve or obtain. Yeah, obtain would be a bit of word here because you're not solving for it, you're just obtaining it. So obtain the characteristic equation of any transfer functions, but within the context of feedback control systems as they apply to spacecraft rotational motion control, we're going to get the obtain the characteristic equation of our closed loop transfer function. Okay, so if that closed loop transfer function is not provided to you, you just look at the block scheme diagram and merge all the blocks together, parallel configuration, feedback configuration, series configuration, and come up with the overall closed loop transfer function that relates the reference signal to the output of the plant by considering the feedback loop, okay? Once you have that closed loop transfer function, what you do is that you look right? This is an I. Look at the coefficients of said characteristic equation. And based on those coefficients, we're going to build the route array, and then we're going to do some analysis based on that, okay? Look at the coefficients, construct the route array, and then draw conclusions regarding the stability or asymptotic stability of the closed loop transfer function. Okay? So that's going to be the bulk of this section. How do we do that in practice, essentially? Now, the caveat to this is that you need to have the characteristic equation of your closed loop transfer function expressed in a proper way. That proper way is this form here. You need to have a coefficient that multiplies s to the power n plus another coefficient denoted by a1 that then multiplies s to the power n minus 1. Another coefficient that multiplies n minus 2. Another coefficient that multiplies s to the power n minus 3, and you get the idea, right? All the way to a n minus 1 that multiplies s, plus just a single coefficient on its own without the variable s. So that is the proper form into which you need to express the characteristic equation of your closed loop transfer function. Why closed loop? Because the objective here is to assess the closed loop stability of everything with the feedback loop included. This tool could be applicable to any transfer functions. Open loop, transfer function of just the plant, just the controller, whatever you can think of, okay? But for practical reasons, what we're going to use this tool for in this course is to assess the stability of the closed loop transfer function. All right, so based on that, you will construct an array that has n plus 1 rows, and the first row will be your Sn, and then Sn minus 1, Sn minus 2, Sn minus 3, all the way to S1, and finally S to the power of 0. Okay? So the number of rows you're going to get in this array solely depends on the order of this polynomial, which is the characteristic equation, which is always, by the way, equal to 0. So you set your denominator equal to 0, and you call this guy your characteristic equation. That's what it is. Okay? So n plus 1 row, and then you're going to fill this array with the coefficients of your characteristic equation first, and then you will calculate the remaining ones. And the way that you're going to fill this array using those coefficients of your characteristic equation is by filling the first 2 rows with them only. And that's why I kind of draw a line here that separates the first 2 rows of this array, which are going to be filled with those coefficients, the A0, A1, A2, all the way to AN. And then whatever we have underneath this horizontal line, where those coefficients here will be calculated. Okay? And the way you fill those 2 first rows with those given coefficients are always the same. We start with A naught here, and then A1 underneath, and go back up with the A2 coefficient, down A3, A4, A5, A6, and if you happen to only have 6 coefficients here, you stop with the last coefficient that is provided to you, and then you fill the remaining one with 0. And then you draw a vertical line, and that is the extent with which the routes array goes to. If you were to be given a characteristic equation with only A naught to A5, then you would stop here and draw the line there. Okay? So you just fill those 2 first rows with as many coefficients that you have, and then you draw the line. You say, enough. I've placed all my coefficients I had in my characteristic equation into the routes array, and that's it. And if, again, you happen to stop here at the top, then you need to fill the next one with simply a 0, like that. Okay. Now the question is, how can you then calculate the remaining elements of the routes array? Well, the very last element that was going to be placed next to the s to the power 0 will always be the last coefficient in the characteristic equation, which is your an. Okay? You can write it down there directly. One less coefficient or term to calculate in this array. That makes you happy. Okay? So if n would have been 6, then it means that this coefficient will be exactly the same as that one. Okay? So you just reuse the last of the coefficient down here. All right. So let's call these B1, B2, B3, and let's see how can we calculate them based on what we fill the first 2 rows with. Okay? So B1, you have to look at the row immediately above, and you get that coefficient A1. And then you do that one times this one, which is kind of crossed to the right. So A1 times A2, and then you do minus the one below here times this one. So in terms of equation, that would be B1 equal to A1, A2 minus A3, A naught. But then you need to divide with what I call the anchor. So the anchor coefficient is always going to be the one in the first column of the row immediately above the row for which you're actually calculating the coefficients currently. Okay? So this minus this, this times this minus this times that over the anchor, which is A1. Okay? That is for B1. A1, A2, A3. Now for B2, it is going to be very similar. So B2 for its calculation is going to rely on the first columns here, as we have used them for B1. But instead of using the second column, then we need to look at the one kind of crossing to its right. Okay, so that would be this column. So B2 relies on this and that. B3 would rely on that as well, but this time those two. Okay, so B3 or B2 would be A1 times A4 minus A5 times A naught over A1. B3. Now you're going to use the first column here with the same two coefficients, but you move the other column further to the right. Okay, in diagonal essentially, always in diagonal. So B1, first column and also based on the column to its diagonal here. B2, first column and the column in diagonal. B3, first column and the column in diagonal with it. Okay, the same idea. B3 will be A1 times A6 minus A0 times 0, or if you had an A7, to generalize this discussion, that would be an A0 times A7 divided by our anchor for that column, which was the element in the first column right above this row. Okay? But for this one, that would be, again, the first column that will be needed to the calculation of this one, and the one in diagonal. But we don't have any remaining elements, or in other words, are all 0, which means that this here will be 0 as well. And as you go down the routes array, you'll see that the zeros will draw a diagonal, and as you go down, you will get less and less entries to calculate. Okay? So let's call these ones our C's. And let's see what we end up with. So for C1, calculation of C1 will be based on the 2 rows above it, okay, those 2 rows and first column, and the column and diagonal again for those 2. It is going to be C1 equal B1 times A3 minus B2 times A1. And our anchor for all these entries is going to be B1. So divided by B1. That's for C1, okay? Now for C2, its calculation, you're going to rely on those 2 again, A1, B1, but now the column to its diagonal is going to be this one. So C2 is going to be B1, A5 minus B3, A1 over the anchor for that row, which happens to be B1. C3, let's do C3. The C3 is going to be relying on the first column here and the column on its diagonal, like that. So it is going to be B1, A7, B1, A7, minus 0 times A1 over B1. And for this one, we don't have any elements. That's all we've got. Okay? And you keep doing calculations like that. Keep filling the rows until you hit the last row. And the entry for the last row is always the last coefficient in that polynomial. Okay? So hope it makes sense. And then, once you fill all the entries for all the rows in the routes array, you're going to have a look at the entries in the first column of this array. Okay? Let's say E. Okay? So you're going to look at all those entries. First column only. And you're going to look at the signs of those. And whenever you're going to hit the sign change, that's going to be an indication that there's going to be one root or one pole, which is going to be either on the imaginary axis or on the right-hand side of the complex plane. Oh no, sorry. It's going to indicate that you're going to get a pole in the right-hand side of the complex plane, and therefore it is going to be an indication that this is related to an unstable system. Okay? So let me put that in words. And not only is this going to be an indication that you have an unstable closed-loop transfer function, but furthermore, the number of sign change you will encounter in the first column will be related to the number of poles lying on the right-hand side of the complex plane. You want to say that number of sign changes in the first column will be equivalent to the number of poles in the right hand side of the complex plane. Okay? So let's do a quick example with numbers to see how can this be applicable to a real situation. Okay? Number of sign changes in the first column, number of poles in the right-hand side of the complex plane. And that's the beauty of it, because you don't need to solve for the poles to know exactly where they are, because if all you need to know is whether or not this is related to an asymptotically stable, a stable, or an unstable closed-loop transfer function, well, that Roots criteria will give you the answer right away without having the necessity to solve for all the individual poles related to that characteristic equation. Okay? So quick example, if the characteristic equation would be 5s cubed plus 2s squared plus 2s plus 1 equal to 0. Well, even before constructing the routes array, one thing you can do is look at the various coefficients. And if there's a negative coefficient in there, or a coefficient equal to 0, that immediately tells you that there is going to be either a pole on the imaginary axis of the complex plane or a pole on the right-hand side. So if that's all you want to know, don't even bother doing the full array. Because just by looking at the coefficients, you will get the indication if they are something on the imaginary axis or on the right-hand side. Let me write it down. So, looking at the coefficients allows you to determine if there are poles either on the imaginary axis or in or on the right hand side of complex plane. And what do you look for here in terms of the coefficients? You want to find coefficients that are either less or equal than 0. So if, say, you would have minus 2s, boom, right away you know that there's something wrong and that you're going to end up with either poles on the right-hand side or on the imaginary axis of the complex plane. You don't know yet where they are, but you know right away that this is not related to an asymptotically stable system by any way, shape, or form, because asymptotic stability implies that all the poles lie on the left-hand side, and no poles shall be on the imaginary axis, obviously. So this is actually for a stable system with poles on the imaginary axis, or unstable system where you have some poles lying on the right-hand side. So right away, because there's a negative sign. Or say, if you would have this plus 1 equal to 0. Now in that case, there is a missing coefficient, right? So we've got s cubed, s squared. Where's my s? So the s term is actually multiplied with 0. That's what it means. And therefore, there is a coefficient equal to 0, and you can draw the same conclusion. And there is something wrong, and therefore that there's either poles on the imaginary axis or on the right-hand side. So either missing coefficients altogether, or meaning that they're equal to 0, or negative coefficients is an indication that there's something wrong. Okay? Plus 2s plus 1. But here, everything is positive. There's no missing coefficients in this polynomial. So let's construct the route array and see what we end up with. Okay? So, building the first row here, s cubed, s squared, s, and s to the power of 0, just 1. Okay? I know I'm filling the first two rows with what I'm given. That'll be my 5, 2, 2, 1, right? Because that is my A naught. A naught, A1, A2, A3. So A naught, A1, A2, A3. And that's all I have. Boom. That's it. Okay. All right, that's a good example. That's not what I have in my notes, but that works out. Okay? So let's do the math here. This one is going to be 2 times 2, 4 minus 5. That's minus 1 over 2 minus 1 half. Uh-oh, that's not a good start. For this one, I'm going to rely on those two and zeros here, essentially. So 2 times 0, 0 minus 0, 0 divided by 2, 0 indeed. Okay, that one is going to be minus 1 half minus 0 over minus 1 half. It's going to be positive 1. And therefore, there is, so we are positive, positive, negative. One sign change from here to here. And then negative to positive, that's a second sign change. So that tells us that there are two poles lying on the right-hand side of the complex plane. And therefore, that this characteristic equation is related to a non-stable closed-loop transfer function. Okay? And you see that I didn't need to solve this equation to know exactly where the poles are, because I don't care. All I want to do is if it is stable or unstable or asymptotically stable, then boom. Just by counting the sign changes, I had my answer. Okay? Now, let's have a look at another example, and let's pretend that instead of a 2, we have the 3, which is actually what I have in my notes here. Okay? Which means I'm filling the top 2 rows with 5, 3, 2, 1, such that this entry becomes 3 times 2, 6, minus 5, 1 over 3, 1/3. This one is 0. Now, for this one is going to be 1/3 times 1 minus 3 times 0 over 1/3, so 1. It's all positive, so all my poles then lie on the right-hand side of the complex plane, and that is then representative of an asymptotically stable closed loop transfer function. This is good. Makes us happy. Okay? Let's do a third quick example with another characteristic equation. This time, S4 plus S3 plus 2S squared plus 6S plus 8 equals 0. Again, we're going to apply this quick trick. I have all my S's, 4 cubed square S and S to the power 0. I'm good. They're all there and they're all positive. So I have to carry out with the analysis to figure if this is going to be unstable or stable, because just by looking at this, I cannot know exactly. I don't know if they are unstable poles or poles on the imaginary axis. It doesn't mean that they aren't, because all of these are positive and are all there. It just means that I cannot draw that conclusion right away. So n plus 1 rows, so S4, S cubed, S squared, S, and 1. Drawing this. I know right away that this entry here is going to be 8. I didn't use that in the previous examples, but that is a quick trick to avoid having to calculate this one. I'm filling the first two rows as per usual. So here, 1, 1, okay? So this here, 1, 1, 2, 6, 8. And I need to fill this one, so zeros. And boom, I draw the line here. This one, 2 minus 6 over 1. That's minus 4. And that one is going to be 8 minus 0 over 1, 8. That one would rely on those two, and those two, which are both 0, so I'm getting 0 here. This one, so minus 4 over 6, that's minus 24, minus 8, minus 32, divided by minus 4, that's minus 8. I had minus 32 by minus 4, that's 8. This one here is going to rely on those two and those two. But because those two are 0, I know right away that the answer is going to be 0. And that's it. So now I have one sign change, another sign change. So two sign changes. That tells me that this characteristic equation is related to an unstable closed loop transfer function, and that's it. As easy as this, okay? So, two sign changes, meaning that I have two poles on the right hand side of my complex plane. And that is not good news. Okay? All right. There are some problems that can happen when you start building a routes array. One of them is when you end up with a 0 of your calculated coefficients in the first column. The problem being that you know that what you calculate in the first column will become the anchor for the subsequent rows calculation. But if you try to divide with 0, you're going to get infinity, and that's an indication that something is not going according to the plan. This is a particular case. If you end up with a 0 in the first column, you have to stop there and apply the following solution. So that is kind of the problem. And the solution is going to be replacing 0 by epsilon, and use that epsilon in the follow-up calculations, and then say the limit of epsilon towards 0 to evaluate all entries within the routes array. Okay? So let's do a quick example that will kind of highlight how this works in practice. So let's say that my characteristic equation, let me start higher up. Characteristic equation would be S5 plus 2 S4 plus 2 S cubed plus 4 S squared plus 11S plus 10. You set that equal to 0. First thing you look if you're missing any S's. So 5, 4, 3, 2, 1, 0. We're good. And the coefficients are all positive, so I cannot draw any conclusions yet. So I need to continue with the analysis. I'm going to construct the array. S5, S4, S3, S2, S1, S0. The first two rows calculated or just provided by the characteristic equation directly. That's my 1, 2, 2, 4, 11, 10. That's it. Draw the line there. 2 times 2, 4, minus 4 is 0 over 2. That's 0. Something is not going according to plan here, because that is the particular case. And 0 in the first column, if you remember. Okay? So I can calculate that one. 22 minus 10 divided by 2. Yeah, 6. And that one is going to rely on those two and those two zeros. So that would be 0. So for this one, you clearly see that I would have 0 minus 12, which would be minus 12 divided by 0 and get a minus infinity. Okay? So that doesn't work very well. So instead, the trick is to come in and replace the 0 with a dummy variable that we shall denote epsilon. Okay? Such that for this entry that I'm going to denote C1, I'm going to get C1 equal to 4 epsilon minus 12 over epsilon, or same thing as 4 minus 12 epsilon. Four minus 12 over epsilon. Okay? That one over here, 10 epsilon minus 0 over epsilon, that would be 10. You try to line them up. Okay? And that one here, that would be 0 as well. We know that the last entry always corresponds to the last coefficient here. So all we need to calculate then is this one. Okay? Then we shall denote D1. Okay? So D1 is going to be equal to this times 6. This is a little bit cumbersome to carry on in the follow-up calculation, so I'm just going to call this one C1 for the time being. So C1 times 6 times or minus 10 epsilon over C1, or alternatively D1 equal to C minus 10 epsilon over C1. But I know that my C1 ultimately was equal to this. I'm going to replace C1 with that. and obtain 6 minus 10 epsilon square over 4 epsilon minus 12. 10 epsilon square, 4, yeah. Okay? So this is for D1. And now I can come in and substitute for epsilon towards 0 in the calculation of C1 and D1 to get actual numbers. So doing so here, 4 minus 12 over 0. 12 over 0 is infinity. So something minus infinity will give me minus infinity. And for D1, I will get 0. That would just be 6. Okay, because that would be 0 over minus 12. So 0. So 6 minus 0, 0. Okay? Boom. And that tells me that I went from positive, because we consider that our epsilon was a positive scalar, that was almost equal to 0. So went from positive to, negative, and then negative to positive, positive, positive. So we got actually 1 and 2 sign changes. Meaning that we end up with 2 poles on the right-hand side, which isn't a very good news, okay? So that is the trick whenever you hit a point in the calculation of the coefficients on the first row, which is equal to 0, right? That was our 0. So we swap that out with epsilon instead and keep carry on with the calculations of the follow-up entries in the routes array. Cool. So let's use this very generic linear feedback control theory, and let's apply that to, again, our particular situation where we are controlling the rotational motion of the spacecraft about a single axis using our faithful modified PD controller. Okay? But then we're going to make things a little bit more realistic, and we're going to assume that between our controller, which is a piece of code running on the flight computer, and the actual physics, is going to be a mechanical device referred to as our actuator. And then we'll see what shall be the response time of our actuator, such that we end up with a closed loop system which isn't unstable by the addition of our actuator. Okay? And on that, I'm going to take a little sip of green tea. Sencha Uchiyama, as always. Okay, so let's go back to a block scheme diagram. I have my reference signal here, plus, minus. This provides me with the error between the reference signal and the actual output of the plant, being the rotational angle in our case. This is being fed to my KP term of my modified PD controller. This term, from this term we then subtract our KDS that multiplies the output of the plant, okay? I'm going to draw my plant over here, which is my 1 over J S squared, my double integrator dynamics. That provides me with my output, Y of S, where Y of S is, as always, the rotational angle. And that typically provides me with the torque that we had applied directly onto our dynamics. But in practice, there has to be something in between a software, which is calculating this value, and the device that is trying to apply this torque onto our physical spacecraft. Okay? And this is where the actuator comes from. You're going to have a box here that transfers this electrical signal essentially into a mechanical action. We'll call this act for actuator. And the transfer function of this actuator is going to be 1 over tau s plus 1. Tau being the time response of our actuator. So if you do the distinction now between the commanded control signal U and the applied one, or the desired torque as calculated by the controller and the applied torque, well, those two won't be equal to each other now because of this realistic mechanical device that doesn't respond instantaneously to what the controller wants. So the relationship between both is going to be first order transfer function with a rise time or response time. So if this is UC coming from the controller, a sharp step command, well, the actuator will need some time to respond to that. Right? The time to open some valve or to spin a wheel or something like that is not instantaneous. And we're going to get a response which is a first order response. So let me just make the distinction here. It's called UC, the line in red, which is the desired torque as calculated by the controller. Let's see. Okay. And say in blue, the physical torque being imparted onto our spacecraft. Like that. That is U. Okay? So it just adds one level of realism to any simulations you want to be carrying in MATLAB Simulink of a feedback control system, but this time considering the mechanical device that will physically produce the torque demanded by the controller. Okay. So that's pretty much what we have. And just for completeness, UC is our control lock. So that is going to be equal to Kp times error minus Kd times theta dot. Okay, because our output here is actually theta in terms of specifics for spacecraft rotational motion, just like that. And you can call this, torque. Physical torque being produced by the actuators and the commanded torque from the controller. Okay, so this would be the torque as calculated within the flight computer, the commanded torque. All right. So then the trick here is going to use the route stability criteria to figure out what should be the response time of our actuator, or what should be tau, to ensure that via the introduction of this new transfer function in here, we don't drive the entire system to be unstable. Okay? So, how can we apply route stability criteria in a practical application? Closed loop transfer function. Closed loop transfer function always with routes, okay? And our context. This is not some random math we're doing. This is engineering and spacecraft engineering. So we want to know if the whole system is a closed loop system will remain stable or not by adding this block in between. Okay. Essentially, the closed loop transfer function can be done in 2 steps. First step is to do the series connection here, and with that in feedback configuration, and then as a second step another series with KP, such that we end up with our open loop transfer function obtained by simply disconnecting this branch will be, okay, so I'm multiplying these two together, 1 over tau s plus 1 times j s squared, and then I'm doing plus kds. That will give me one transfer function here, but then that one needs to be multiplied with kp. There you go. Okay, so that is your open loop transfer function. But now we want the closed loop transfer function, and you should know by now that the trick is, well, close the loop obviously, is to use the open loop transfer function over 1 plus open loop transfer function, like that. Okay, let's do it. So we get for G closed loop, we get open loop plus 1 times j s squared plus k ds. This over 1 plus the same thing over again, kp over tau s plus 1 times j s squared plus k ds. I'm going to put everything onto the same denominator here and then cancel it with that on top to simply get kp over tau s plus 1 times j s squared plus k ds plus kp. Yep. Okay. And because I know I want to use that within the route stability criteria, I know what kind of format I want for my characteristic equation, right? I want, in that case, my s cubed, s squared, s to the power 1, and s to the power 0 at the very end. So therefore, I'm just going to write the closed loop transfer function as being obtained by multiplying these two terms together to begin with. So that would be tau j s cubed plus j s squared plus k ds plus kp, which means that my characteristic equation for this closed loop transfer function that was obtained from the double integrator dynamics, the modified PD controller, and the actuator, which has a first order transfer function in terms of response, will be equal to tau j s cubed plus j s squared plus k ds plus kp. And never forget that your characteristic equation is always equal to 0. Okay? So that typically we solve the characteristic equation for the roots or the values at s that will make this equal to 0. And from there we get the poles. But this could become a little bit complex when you go to orders higher than 2. So again, the main benefit of using the route stability criteria is that we don't need to solve for the roots of the characteristic equation, or we don't need to know where the poles exactly are in the complex plane. All we want to know is this transfer function representing the entire system in a closed loop fashion will be stable, unstable, or asymptotically stable. Okay? Well, first off, quick trick again, you look at the coefficients to make sure that there's no missing or that you don't end up with a negative. So we have our s cubed, s squared, s, and s to the power 0. So they're all there. And furthermore, they are all positive. So we cannot draw any conclusions at this stage, so we need to do the full array. So we have s cubed, s squared, s1, s to the power 0. Oh, that's going to be a quick one, right? Because we know that we fill the top two rows with the coefficients of this polynomial. So it would be tau j, kd, kp, and that's the end of it. Draw the line here. This entry will be j kd minus j tau kp over j. Okay? And because this one would rely on the first column and the third one being two zeros, I know that I'm going to get 0 here. And I know that this entry will be the last one in terms of coefficients here, and that is my kp. So that was easy. So I'm just going to divide numerator and denominator with j. We get kd minus tau kp. Nice. If you happen to have designed your modified PD controller correctly, you will always end up with Kp and Kd being positive values. Okay? So this is going to be a positive value here. The J is the inertia matrix along that axis of interest, or inertia, principal moment of inertia, positive. The response time better be positive as well. We're talking about 0.1 seconds in terms of how long does it take for the actuator to reach the command, or 1 second or 10 seconds if that happens to be a very slow actuator. Yet tau will be a positive number. So everything is going to be positive here. The only unknown to ensure that everything remains asymptotically stable is this one, right? Because as per the route stability criteria, we have that this, if we don't want any sign change, better be greater than 0. Okay? Which means that if this is positive, well, we know that Kp and Kd are positive, okay? So the real constraints here is going to be imposed on the tau response time of the actuator, which will be tau has to be less than the ratio of Kd over Kp. Or in other words, you want a response time of the actuator which is fast enough to ensure that it can keep up with the commanded torque as calculated by the modified PD controller. Because if this guy happens to be a large number, it will mean that your controller might be demanding this, and then that, and then this in terms of a signal, such that the actuators, if it is too slow to reach the first command, boom, I reach it, then by the time we're here, it's already one kind of step up command in the past, right? It means that would have neglected that one. So that would be a very bad actuator. It's way too slow to respond to what the controller wants. So a better actuator would be one that tracks the demand of the controller very quickly. Boom, boom, boom. Okay? That's way better. So as close as you can get the output of the actuator to match its input, it's always better. Okay? And that would be the constraint here to satisfy, to ensure that not only you get a good actuator, but one that will not drive the entire system to be unstable. Because if that inequality is not satisfied by the choice of your response time for the actuator, then that will mean that this would become negative or equal to 0, but probably negative. So you get 1, 2 sign changes, and that would mean that the entire closed loop system will go to garbage because you're driving poles onto the right-hand side of the complex plane. Guess what? You've lost your job because you've been creating the cause of the loss of your spacecraft. Multi-million-dollar mission done because the actuator was too slow to respond to the controller's demand. Okay? So that's just a quick practical application of this very, very powerful tool known as route stability criteria, which again is all about inferring about the stability of the system without having to solve for the poles individually. Okay? Hope that helped you again bridge the gap between theory and practice, and in practice here in terms of spacecraft rotational motion control. Hope you're following along with your loose piece of paper that you're scribbling equations on, drawing block scheme diagrams, drawing figures, things like that. Hope you're having a blast, and I'll see you next time, guys. Bye-bye.